Now, I call this, and I have, in order to sort of imagine this, I think of a piece of matter, might be some H2O. If I superheat it, you see, so that the particles are so far apart that the interaction is no longer matter, that's S lower star. I think of that as the Avogadro version. So when you talk, it's the substance, right? The fact that it's H2O is a property of the dot, a property of the atomic numbers or whatever it does exactly, the molecular structure at each dot. It doesn't matter whether it's heated up like that. You know, that a little sample of water is dispersed throughout the whole solar system or whatever. It's still H2O. But it's essentially one of these dots, one of these things where every connection is a loop. On the other hand, if I freeze it, and then I superheat it, superfreeze it, or push it way down, I get supermolecules. So this is the Bose version. You get the supermolecules by merging the atoms, but not losing their, all the interactions became now self-interactions. That's S lower street. And there's a natural map again, because we have a full inclusion of two editor, which says always you have a natural map, which I call cooling. In other words, if you do these two experiments, superheating and supercooling, but there's also a relation between, a partial relation between them. Sort of, you know, Van der Waals describes what happens when you cool something, it passes through a change of state. But anyway, that's not quite what happens here, but certainly there's more information in the fact that in this supermolecule, some of those loops were already loops before, whereas others were not. You see, so that distinction you would not know from just the two objects, but it's specified by the economic map. So, yeah, so this construction is fundamental to the type of analysis. Now, I want to think of these L's also as infinitesimal. In other words, there are many features that infinitesimal objects have, and especially in the differential geometry, they have still more special ones. But to some extent, let's say I'm investigating hypothetically, what will occur if I just assume that infinitesimal means object in this subcategory L. So in other words, the graphs that consist only of loops, those are the infinitesimal graphs and so on. So it will turn out that there are many properties that you respect of infinitesimals, and this is a useful way, maybe. Maybe it's too general, but it's useful because it's pretty restrictive anyway. So I think of this as, here comes another, I don't think Grossman showed how to do this. Maybe he did. He did a lot in 2 pages. But to derive the notion of equality from this setup, continuous versus discrete, different versus equal. I want to call this Q here. This Q is, again, a essential geometric morphism, but it has this property that Q lower star equals Q lower Q. By construction, I just took those objects for which it was true. And then P is equal to QS. Q is just P except restricted to those objects. But for them, the two sides are the same. So I want to call that equality type. Why the hell I want to? Well, you see, because S is equality. S is equality, which is valued in the type Q. And equality is substance. This sample, what did it consist of? H2O. Well, that's the substance of it. So, in fact, you see, so, wait a minute, let me just write this down somewhere. So Q, the two adjoints are the same for Q, so it's equality type. You know, it's like K theory. The idea is if you want to measure the objects in a category, you have to first figure out where it's going to take its, where the measurement is going to take its values. Because they probably won't be simply natural numbers or something. What that is will depend on the category. So the measurement of equality will first have to be specified as another category of this special type relative to U. And then the actual process of measuring also. So the point is that this the quality, right? The S Q lower star is the same as Q lower shriek, but I want to write it that way because I want to say that this is S following P lower star. So in other words, is that the functor that measures the quality preserves the points aspect. Doesn't preserve the pieces aspect at all, because the thing is still made out of the same substance no matter how many pieces there are. So it's a functor to, I mean, I'm talking about mapping. P is really a string of adjoints, so is Q a string of adjoints, but Q is a collapsed string. So if I'm considering mapping, I'm not just mapping one category to another, I'm doing it in a way that's somehow related to these strings of adjoints. But the special property is that this one is compatible with the points. If I extract the graph, part of the graph, it's just only loops. Still has the same points as the original graph. I preserve the points. So I call that intensive quality. By the way, Grossman, you see Grossman correlated things being equal with intensivity. So quality in general refers to mapping to something where the adjoint string is collapsed. Intensive quality refers to doing that in such a way that preserves the points aspect. So because there's the opposite difference, it correlates with extensive. So there are also extensive qualities. And in fact, the left, this is really S lower star. That's what I wanted to say. S lower shriek, the Bose construction in that picture, is an extensive quality because it's compatible with component, with pieces. Rather than with points. So mapping an adjoint string to a collapsed adjoint string, these are two special cases. One where it actually preserves the leftmost adjoint, and the other where it preserves this other, the right adjoint, the points. Now, okay, this philosophical idea of equality and difference, I think what we've done here, the idea of equality has been sort of refined to nearly equal. inside, oh, by the way, when I say these spaces are infinitesimal, I mean their components, they're big, but they're made out of infinitesimal stuff. With no connection. It isn't that they are as spaces. I mean, they're made up of tiny pieces. But I found it more convenient, just to, if you like, it's a matter of convenience, consider sums of infinitesimals and call it infinitesimal stuff. Should have said that before. But so it's about being very nearly. See, Euler says an infinitesimal is zero, and yet it's not zero. Okay? So it's equal to that point, but it's not equal either because the little cloud around it doesn't consist only of zero. So these things that people say are nonsense in Euler, you already see it's very profound. You're at the point, and yet you're not at the point. Depends on whether you take the underlying U or you take the L itself. So nearly equal. It's somehow connected with things being nearly equal. With equal within that is a special case. But it's not different. You can't say that it's different because there's only one point there. So I think of this as kind of, between Heraclitus and Cratylus. Heraclitus says you can't step in the same river twice. And then Cratylus, in order to provide fodder for his son, his pupil Plato, said, well, you can't even do it once. Of course, he's wrong. You can do it once, but while you're doing it, you're also doing something else. The river is doing something else. It's moving a little bit. So the fact that when if you think of a map from one of these infinitesimal objects to X and say it's one with just one point, then this is stepping in, let X be the river, and you're stepping into the river. Well, you are doing it at one point because there's only one point that you get as a composite. And yet, the map itself is certainly more than that point. It's just telling you where the whole thing goes. But you wouldn't want to say that X is different from that point because there's no other point for it to be at in the time parameter. Okay, so I think this is the best solution to the Heraclitus idea. That this canonical map is an isomorphism. So these are the germs of motion, et cetera, et cetera. All right.
If you want to make a break sometime, but it's
Make a break. Yeah, okay. No, well,
but it's not necessary.
I know. No, let me see. What do we do about that?